Okay, so we have a few things that we're going to be doing today, one of which is going to be wrapping up our group work. So that's why you're still sitting in your groups. But I want to remind you that we have a quiz on Wednesday. And so that quiz is kind of covering the stuff that we've done in chapter 4 plus the solution stuff from chapter 3. So figuring out what is the concentration of something and using the concentration to find moles of something. So what I want to do is take a look for a moment at the board here as an example of some of the types of things you might need to know. Okay, so this doesn't explicitly state all of the things that we're going to have to do, but let's just start with, it gives us a sentence, and here, this gives us a sentence of a chemical reaction. So the first thing that I want to do is take a look at the idea of going from a sentence to a chemical equation. So we have gaseous dichlorine monoxide decomposes readily to chlorine and oxygen gases. So first chemical, what are you going to write down? So chlorine 2 and then 1 oxygen because it's dichlorine monoxide. Okay, do we have any other reactants? No. Hope, why don't we have any other reactants?
Because it's a decomposition, which it splits into two.
Yeah, it's a decomposition reaction, which means that I only have one reactant. It's going to split into 2 or more products. And so it tells us that we have those products. So I have the Cl2O, then an arrow, and then I have my products. And it tells us those products are chlorine and oxygen gases. So what am I going to write down for chlorine? Cl2. So we have to remember that that's one of our diatomics. Remember on these periodic tables, it's the dark green. It looks like a 7 there, or you can remember Brinkelhoff with the bromine and the iodine and the Cl and so on and so forth. So it's Cl2 plus what? How do we write oxygen? O2. And then it indicates that all of these are gaseous. So since they're all gases, we could put that G in there to indicate that they are gases. So this would look something like this. Okay, if I asked you to write the equation that goes along with that, I didn't put the gases in there, but the chemicals are there. And then I might ask you to balance it. So you're going to need to balance some equations on your quiz. So what do I need to balance this equation? The oxygen on the left-hand side, I only have 1, and on the right-hand side, I have 2. So what am I going to do? Put a 2 coefficient in front of the reactant. So it's going to be 2 Cl2O. All right, so that gets me my 2 oxygens. Somebody else, what do I have to do next, if anything? I see. 2 in front of the Cl right here. Okay, and that will balance it. Okay, so those are 2 kinds of things that you might be asked. Then the question asks, which of the following circles best depicts the product mixtures after the decomposition? What would you say? So by showing of your fingers, 1 is A, 2 is B, 3 is C. Raise your fingers and tell me which circle. Okay, yeah, A, I would agree with that. Kenneth, why do you think it?
There's 2 oxygens. There's like 2.
The reds are paired?
Yeah, there's a pair of greens.
And then the greens are paired. So both of those are showing that each of those chemicals is diatomic, whereas these have them separated into individual atoms, right? Okay, so I'm gonna, ideally I would have more time to spend on this, but we do have to keep moving along. So, how many of you have seen Bloom's taxonomy before? No, that's kind of surprising. So this triangle represents the kinds of things we do in learning and how they build on one another, and how difficult they are. So the bottom level is the easiest level, remembering something. You know, you learned your phone number at some point. You learned your address. You learned your name, for goodness sakes. Remembering something, especially something you use a whole lot, is kind of the lowest level. You don't have to do anything with that. The number that is your phone number doesn't really have any meaning behind it. We can't like use that number to figure out what your hair color is or any of those kinds of things. So remembering is just kind of a basic memorization thing. It's also the easiest to lose. So if all you do is memorize things and then don't look at them for a month, later it's going to be harder to remember them. But if you are understanding them, which is the next level or some of the higher levels, then it'll be easier to remember. So understanding includes things like classifying, describing, discussing, if you're in an essay question, discussing or explaining, identifying. So I might say identify an alkaline earth metal. So first you have to remember what I mean by alkaline earth metal, but understanding what I mean by that, then you're going to have to identify which of those elements might fit into that category. Then applying. In order to apply something, you have to have understood it in the first place. And so this is a lot of problem solving, and this is where a lot of people struggle with story problems in math and the problem solving that we do in chemistry. Because if you don't remember vocabulary and understand the concepts, it's very difficult to apply those concepts to the mathematical processes, okay? And then the next level is analyze. We're going to be doing a little bit of that in your group work, where you're doing a little bit more than just understanding, but you're comparing and contrasting. You're trying to determine what things matter, what things don't matter, and how they fit together. And then finally, evaluating would be determining which one's better now that I have, you know, these two models, let's say, of what's going on. So I've given you at the bottom some hints of things that you can do if you are struggling to either remember rote knowledge, understand concepts, or process skills, which kind of fits into the application. So if you're finding that, yeah, I remember all of my vocabulary, but I don't know how to do the problems. Well, what you probably need to do is just practice a whole lot. That's kind of the thing there. On the back is what's called the study cycle. The study cycle has been developed by many different learning scientists as a really good way to learn. If this is a class that is important for your career, you really want to pay attention to this. If you have another class that is important for your career, you want to pay attention to this. Now, a lot of people jump right to number 4, which is studying, and studying is great, but steps 1 through 3 are also important. Previewing is before you go into a class, even if it's just 5 minutes, taking a look at what are you going to be talking about that day. That might be looking at your notes from the previous class. It might be scanning the topics in your text. So we're going to be getting into section 4.3, making sure you go over that. That's why I tell you what the reading is. That's why I tell you do the prepare to learn. So it gives you that opportunity to look at that ahead of time and kind of have your brain primed. Attending class, great, you're all here, fabulous. But in addition to attending class, you also need to be taking good notes and engaged in active learning. So not just writing down everything that I put on the board, but thinking about it. Do I understand this? Ask questions. Ask questions in your group. Talk to one another. Ask me questions. And then reviewing is also important every day after class. Doesn't have to be right after, can be in the evening, but after class, go through your notes, make sure you understand what you wrote down, fill in anything that you were missing. Those 3 steps are going to make it so much easier to study when you get to that. Then when you study, a lot of people don't know exactly what studying looks like. So at the bottom, there is a description of an intense study session. Does not need to be 4-hour breaking your back. It's figure out what you want to accomplish, do the thing, take a break, then ask yourself, did I do the thing? Maybe your thing is, I need to memorize those polyatomic ions because I know they're going to show up on that quiz on Wednesday, because they are. Then spend a half an hour making flashcards, going through the flashcards, take a break, and then come back and then see how many of them you can write down without looking. So that's the kind of thing that you would have for an intense study session. Obviously, you can't learn all there is in chemistry in a half an hour, so you're going to have more than one of these between now and Wednesday.
It's still just the bold points, right? Or is it all like that?
Bold polyatomic for right now, but also bold acids. So anything that's in bold. Okay. So hopefully that might have given you some ideas of changes that you can make. If you're not getting the grades that you want, maybe you can make those changes. If you're not sure how to implement these or what to do, come and talk to me. We can go over that. We need to pull out modeling double displacement chemical reactions. So you have looked at the ionic solutions last Wednesday. That is what we call our target. We are trying to understand what's going on in those bottles, but we can't see ions. We can't see the water molecules that surround them. So we are going to have something that is analogous. So an analogy is something that is like the original that helps us to understand. And our analogy is going to be these blocks. So I want you to pull out these blocks. Everybody grab a couple of them and take a look at them. Feel them. And you should have 2 containers with blocks. So you should be able to have plenty of blocks for everybody to share. This is our analog or our model. That's another way to talk about it. So one of the things you're going to do is try and use this model to understand how ionic compounds form. The other thing that you're going to do is try to figure out, and this is that higher level thinking, you're going to analyze what makes this a model for ionic compounds. How are they similar? And in what ways is it not like an ionic compound? So some ways are going to be unimportant. Some ways might be important. Okay, so just as a starting out point, you will discover that I have used color to indicate something about the ions. And so that's one way that we might have some similarities. But another way is that, well, the ions don't actually have that particular color. It's just a way that I'm showing all the positives are alike in one way and all the negatives are alike in another way. Okay. So I want you to take about 10 minutes to try and finish the back side of your sheet on the modeling double displacement reactions. And if you have, if you need to finish what's on the front, you can go ahead and do that. I will collect one of these. So if you had an extra sheet in your folder, you can put it on the extra sheet, or if somebody just wants to turn in their copy, that's fine. Just make sure that everybody sort of agrees upon what's going on there. Okay, I want to pause you all for a second and take a look at the chart that is on the back. So it's divided into 2 sections. And remember that when it says target, that's the real thing or ions, and the analog means the blocks with the Velcro. It's the model. So it first asks you to look at your original compounds. So there are lots of things that you might have noticed were similar. One thing one group pointed out to me was that the ratio of the blocks should be the same as the ratio in the formula. So what I have is FeCl3, and I have a ratio of 1 Fe to 3 Cls. So that ratio is the same for the compounds. Then I want to look at what are some of the differences, but I can have two kinds of differences. I can have something that is true of my block, but isn't true of the ions. So for example, ions aren't really wooden blocks, right? Ions don't really have color. Now, those aren't really important differences for our understanding, because I doubt that you will somehow integrate wooden cubes into your understanding of ions. You won't start picturing ions as wooden cubes, so I wasn't too worried about that, okay? Then I can have the other way around, where I can say, well, what's something that is true of an ion that's not true of the blocks? And so sometimes those might be important differences, and sometimes they might not be. So one of the things is that if I had a positive and a negative charge that I brought really close together and they actually were ions, what would happen to them? This were really positive and this were really negative. Tyler, what would happen? They would start coming together and join, right? They would move. But if I put these two blocks on the table and rested them near each other, are they ever going to get any closer? No. So they're not actually attracted to one another. That might be something that could confuse somebody, because they might be thinking, well, these blocks aren't coming together, so maybe that's how ions work. They actually have to be touching, which we need to understand those are differences so that this model can be useful to us. So one of the things I wanted to you to notice, how did I distinguish between positive and negative ions? There are a couple of different ways. One way is the color. So you may have noticed that in both sets, there was some shade of blue that was for your negative ion, and there was some shade of red or pink that was for your positive ion. One of my markers ended up making it look a little bit orange, but it was supposed to be red or pink. What's another way? The type of Velcro. So your anion should have had the fuzzy stuff. Your cation should have had the prickly stuff, okay? So as a consequence, if we look at, no, I don't have it in front of me, but question 4, can you make a generalization about which blocks stick together and which ones don't?
Negatively charged ions always stick with positively charged ions.
Okay, so that would be true of ions, but the blocks representing the negatively charged can only stick to the blocks representing the positively charged. So for number 4, we're talking about the blocks. So I might say the blue blocks will stick to the red blocks, but they won't stick to each other, right? Or I could say the fuzzy blocks will stick to the prickly blocks, but they won't, the fuzzy blocks don't stick together. So if I try and get, whether I try and do 2 irons, these don't really stick together. Or if I pull out my other ion and try and get the iron to stick to the lead, the red ones just don't stick together, okay? Then the next question asks what the colors represent. So we already talked about that. And then the next one says, what statement can be made about which ions can form compounds? And so this is just putting that question 4, instead of saying in terms of blocks, now we're going to say it in terms of ions, which is what Tyler originally said. The positive will stick to the negative, but the positives don't stick together, or the negatives don't stick together, okay? So on the chart down below, we talked about the individual compounds. Then there's a column that says observations of the mixtures. So one of the things that you might pay attention to, and this is where you're going to like put all of your blocks in the same box and mix them up, or put them on the table and kind of stir them together. And then notice which ones stick the most. And hopefully what happens, but it doesn't always work out this way. Hopefully what happens is that your ions that tend to be less soluble, so a lot of you have lead or silver, those are going to start sticking very easily to an anion, hopefully the anion that is less soluble. And then the cation that is more soluble is going to be less sticky, and if you attach it to something, that's not working, should be easier to break off. But it's an imperfect model. But it's easier to pull this apart than it is to pull this apart. This one's a little bit more strongly attached because it's the lead, okay? So in the mixture, what I was trying to show is the insoluble compound that results is harder to pull apart than the soluble compound. Does that make sense? All right, and then for some of the differences, you may notice that sometimes things stick together that weren't really supposed to stick together in the mixture. You may or may not have had the appropriate ratio for your compound. So I might not have enough nitrates to go with the irons because I didn't have enough nitrates on my lead to go with my irons when I mix them. So that might be a difference there. Anybody need help in finishing up the chart? All right, try to wrap that up in about 2 minutes. All right, let's take a look at this reaction. Does it look like we switched partners appropriately? Do we have a positive with a negative in each case for our products? Yes, good job. Did we take care of charge balance? +1, -1, that one's good. +1, -1, that one's good. Okay. I only have one objection to this. We didn't show what the precipitate was. So how do we show the precipitate?
Put which one's solid?
You put which one's solid. So what do you think? Is the potassium nitrate going to be the solid or the silver hydroxide? Which one's going to be solid? You think the silver. And that's true. Both hydroxide and silver are almost always insoluble. So this one just should say S here. Okay, so that's the kind of thing I'm going to be looking for on your quiz. Let's take a look at this one over here. We've got silver nitrate and zinc chloride. We switched partners. So did we get positives with negatives? Yes. Did we charge balance appropriately? We didn't charge balance appropriately. Okay, so this is a 2+, and I know that because I have 2 chlorines, right? Chlorine is a -1, but we said earlier that nitrate is a -1. So how do I charge balance that? Do I need more zinc or do I need more nitrate?
Or nitrate?
More nitrate. So I'm going to put parentheses around the whole thing and put a 2 there. Okay, so my silver was a +1, and I can tell that because it was paired with this nitrate. And then we said the chlorine was a -1, so I actually don't need a charge there. And then I didn't indicate which one was going to be the solid, so which one's going to be my precipitate in this case? Any ideas? What did we say over here? We said this one was the solid. Why? It is insoluble, but what would be a key indicator that it's insoluble? The silver. Yeah, silver is usually insoluble. If you see a transition metal like zinc, so silver is the exception to this rule, but if you see something like zinc or nickel or iron, there are no rules for those. You just have to look at the anion. Whatever the anion usually does is the truth. Silver, if you see it, it just matters whether this is always soluble or not. So chlorine doesn't fit into always soluble, so that's going to be a solid. All right, zinc sulfate and sodium sulfide. Did we pair up positives and negatives? Yep, so that's the first thing that I look for. Second thing is, did I charge balance? So here, zinc is a +2. That's one that it's always +2. Sulfur right under oxygen, would that be? -2, so that looks charge balanced. And then over here, I have 2 sodium, so it looks like they at least were paying attention to that. And sodium is a +1. What is sulfate?
-2.
-2. Another good one to have memorized for your quiz on Wednesday. I've been telling you, bold ions, you need to know the formula and the charges, and it's going to keep coming back. All right, so that looks charge balanced. And then they indicated that this one would be the solid. And so I said, if we have a transition metal like zinc, mostly we're just going to pay attention to the anion, and the anion sulfide is usually insoluble. And we know sodium is always soluble. That one is correct. We've got, this one's really tiny, so those of you on the other side of the room might not be able to see it, but we've got lead nitrate and potassium hydroxide. We switched partners. We do have a positive with a negative. And so we have lead and 2 hydroxides. Is that appropriate? So since the lead is with 2 nitrates here, that tells us lead is +2. Hydroxide always has what charge? -1. Another good one for your quiz. All right, so that's perfectly balanced. Over here, potassium is a +1, nitrate is a -1. So what should be the ratio? 1-to-1. So we missed that one. There we go. Okay, and then we've indicated both are aqueous. Which one should be our precipitant? The lead hydroxide. Both lead and hydroxide are usually insoluble. So we're going to put an S there indicating that it's a solid. The one up here, we have potassium hydroxide and nickel sulfate. So now we have K2SO4 because potassium is a +1. Sulfate we just said was a -2. So that's combined together. And then we've got nickel. Well, nickel is one that can change. So I look over here, this sulfate is a -2. So that means the nickel has to be a +2 so that they're balanced because there's one of each of them. So nickel's still a +2 over here. And my hydroxide I said was -1, and there are 2 of those. So that looks good. So I have potassium sulfate and nickel hydroxide. So they say that the nickel hydroxide should be the solid. Is that correct? Yeah, hydroxide is usually the solid. The other thing we can look at is potassium. What do you think? Always soluble. Group 1, always soluble. So it can't possibly be that one. Okay. So you may want to, before you leave, go through these and make sure you have written down those examples and can do that kind of thing. Okay. Okay, I want to take a look at stoichiometry. We talked about this a little bit last week. This is in section, so here we have the learning objectives for this particular section. And that can help you to understand what is it that I want you to get out of the section. That is a good thing to do as kind of a preview for what's going on in the class. Where is it? Okay, so explain the concept of stoichiometry. How many of you feel like you could explain to somebody else what stoichiometry is right now? Okay, so that's something most of you really need to work on. Use a balanced chemical equation to derive the stoichiometric factors. We talked a little bit about that stoichiometric ratio. Do you remember what that was? Do you think you could come up with a stoichiometric ratio? Okay, so that's something that we want to learn how to do. And then performing the calculation. So if we can't do the first 2, you probably aren't going to be able to do the next one. But those are the goals that we're going to be looking at over the next couple of days. Okay, so what I want to do is take a look at what is stoichiometry and back there. Pull this up. I'm going to start with a question that might be like what you see on your quiz. Here is a sentence. How could we put this into a chemical equation? Gaseous dichlorine monoxide decomposes to chlorine and oxygen gases. Okay, so what would I write as the chemical reaction for that, first of all? What's my first chemical I'm going to write down? Cl2O, because it's monoxide. Okay, is that going to be the only reactant? Yes, because it decomposes. So we know decomposition, there's only one reactant. So I'm going to have an arrow, and then it says it decomposes to chlorine and oxygen. So what's the chemical formula for chlorine? Cl2, because it's one of my diatomics, and O2. And then we could put, because they're gases, we could put the little G with each of these. So we're going to have something that looks like this. I might ask you to balance this. So what would you have to do to balance? Okay, so the left needs 2 because on the right, I have 2 oxygens. So in order to have 2 oxygens on the left, I have to put a 2. It's going to go out front, right? The very first thing. That's going to end up giving me 4 chlorines. So I have to put a 2 in front of the chlorine on the other side. So this is what it looks like when it is balanced. Okay. Then the next question is a little bit higher order because it's asking you what it's going to look like afterwards. And we don't have necessarily the right ratio. So we are going to have, this one, it's less about the ratio, but the combination. So which of these 3 looks like the gases that we wrote in the equation? A, why A? Because they're all diatomic. Okay. Stoichiometry. Chemical equations represent moles of molecules. So when we are trying to do our reactions, we are looking at, you could think of them as individual molecules or those big groups of numbers, moles of molecules. So we always have to go through moles in order to figure out how many we need of one thing versus another. I'm going to pause here. Yeah, this is a good place to stop. I'd hope to get a little bit farther. We will do that on Wednesday. Wednesday, what we will focus on before the quiz is how to get to moles. So what you might want to look at is if I have a mass, how do I get to moles? If I have a volume, how do I get to moles? All right. Okay, I'd like to start with a definition. So this is kind of a cumbersome definition, but I've got sort of a generalization down below. So stoichiometry is using the relationships in a balanced formula or balanced chemical equation to determine how much of one chemical reacts with, produces, or is formed from a certain amount of another. So basically that's saying how much of chemical B is related to a certain amount of chemical A. So we might say, how much of one reactant do I need to react with another? So that's your reacts with. You might say how much of a reactant will produce a given amount of a product, or you might say, well, how much of the product will I form from a given amount of reactant? So there's several ways that you can look at this. But basically the idea of stoichiometry is you are going to be looking at the ratios of the balanced formulas or equations, and you will be given information about one chemical in order to find out something about another chemical. So an important thing to remember is that chemical equations represents moles of molecules. So it might be helpful at this point to be thinking about just the molecules themselves or formula units of the inorganic or formula units of the ionic compounds. But basically when I say that I have the coefficients of 1, 5, 3, and 4 in this chemical equation, that relates to how many molecules that I have. Now remember, moles is kind of like a dozen. So if I have one molecule reacting with 5 molecules, that means 1 dozen will react with 5 dozen, and that 1 mole will react with 5 moles. So that's why we say it goes to moles. So every time we are doing a stoichiometry reaction, we're going to need to find moles. Now you already have 2 ways of finding moles. So this is an illustration of that principle that you have to find moles. So on the left side, we're considering this like a strip mall on one side, and on the right side, there's a different strip mall. And in order to get from one to the other, you have to cross a really busy street. So you're not allowed to cross just anywhere. You have to cross at the traffic light in order for it to be safe. And so in our case, the traffic light is the mole ratio. We have to go through moles. So we've got a no pedestrian crossing sign at the top there. We can't go directly from mass to mass. You have to translate to moles. So everything that you do with stoichiometry, you're going to have to go to moles first, and then switch from one chemical to the other. We have one way of doing this. Let me back up. We have one way of doing this if we have the mass of the compound. So if I have the mass, then I need to divide by the molar rate. That's what that kind of fancy M there is supposed to represent. So mass divided by molar rate will give me moles, but we've also talked about solutions. So if I have the volume of a solution, then I'm going to use the molarity to get to the moles. We have 2 different ways to get to moles. So when in doubt, we're going to find moles, because that's going to be the first step in getting to a stoichiometric ratio. So the moles for solids, if I know my material is a solid to begin with, I'm going to divide the mass by the molar weight. If I'm given a solution, like in lab last week, you had the sodium hydroxide and you had the hydrochloric acid, you didn't have molar weights of those, but you had the concentration. So you're going to take concentration times liters. So it just says volume there, but remember molarity is per liter. So you're going to have it in liters in order to translate out of into moles.